We will partition an array into the minimum number of contiguous subarrays so that each subarray sum is less than or equal to capital S. Among all such minimal partitions, we will maximize the minimum subarray sum. Here is the problem summarized in two objectives. We start with an example. The array is 4, 2, 7, 1, 3, 5, and the cap S equals 9. We will build a partition with the smallest number of subarrays, each with sum no more than 9. We scan left to right and keep adding until the next element would exceed S. At that moment, we cut. This greedy rule yields the minimum possible number of segments. Watch the running sum. We reset the sum when we cut. Among all partitions with k segments, we want to maximize the smallest segment sum. We compute the segment sums and highlight the minimum. Then we try a different valid partition with the same number of segments to see how the minimum changes. Greedy cutting only when the next element would exceed S gives the fewest segments. Intuition: if you cut earlier, you would only create more segments or force smaller sums without any benefit. We visualize an early cut and see it cannot reduce the total number of segments under the sum cap. To maximize the minimum segment sum, let T be a threshold. We ask, can we partition into at most k segments so that every segment sum is at least T and no segment exceeds S? We binary search T. We test T equals 7. Then we test T equals 6. We first compute k by greedy. Then we binary search T between the minimum element and S. At each step, we greedily check if we can build segments with sums at least T and at most S, using at most k segments. This runs in order of n times log of S, since each feasibility check scans once. For our example, the minimal number of segments is 3, and the maximum achievable minimum segment, sum among those is 6.